Hello. Hello everyone. I hope you're all doing great. So my name is Bouzekri Sheima. I am student in the Faculty of Hydrocarbon and Chemistry. Currently, can you hear me?
Yes, Shemo.
Yes. Okay. So currently, I have 3 years studying transportation and distribution of hydrocarbons, and I am a member of the development and training unit in the SPE student chapter, University of Boumediene. So thank you everyone for attending our online lecture with Sir Mohamed Amrouche. Before I ask Sir to introduce himself, I will just remind you of some key rules that we are going to respect it during the lecture. So guys, please keep your mic off during the lecture and don't hesitate to write your questions in the chat box. And Sir will answer all your questions. That is all. Thank you so much. And now the microphone is yours, sir.
Thank you. Thank you very much, Shaima. So before starting, can you please confirm if you can see me on the cam, you can hear me clearly, and you can see my slides?
Yes, we can see.
Yes, sir.
All good. Thank you very much. Okay, so thank you. Thank you very much for SPE, University of Boumediene Student Chapter, for this kind invitation. It's always a great pleasure to share what I'm doing with you guys. In today's lecture, I would like to share with you something a bit extraordinary, I would say, or not very common, not very usual. And it's a topic that really I'm really enjoying doing this kind of work actually on this topic. It's Introduction to Planetary Geophysics, the next frontier of subsurface exploration. This is how I titled my lecture. So in this presentation, I would like to share with you some introduction and insights on what is being done as research, as work on planetary exploration using geophysics on the moon, especially on Mars. And so we will, I will try to basically cover all the introductions, all the keys that you need to help you to understand what is happening now in the current status of the planetary exploration. Right, so this is the outline of my presentation today. I will first start with the what we call the new space race. As you may not noticed, there is a huge international interest on space exploration recently. So we are going to overview all the motivations behind this engagement towards space exploration. And then we are going to focus and talk a little bit about science. We are going to do some introduction on lunar geology. The moon is our closest celestial body. It is the most studied, and it's very important to have a good insight on the geology of the moon. And then I'm going to talk about geophysics, what kind of geophysical exploration, what kind of data do we have from the moon, and exploration as well for Mars and Venus. And finally, I'm going to share with you guys some published case studies I worked on, I published using geophysical data on the moon and Mars. All right, so without further ado, let's jump into the presentation, the new space race. As you may notice, recently there is a huge international interest from the international community on the space exploration, especially with the advent of the private sector. There are many private companies investing on space exploration, developing technology, try to get out of this planet to get something from there. We can name few, like for example, SpaceX or Virgin or Blue Origin. These are main players from the US investing on space and on how they can build a more robust or more efficient means to go to space. Also, we witness the involvement of new players in the space exploration. Before, during the 60s and the 70s, it was USA versus Russia or Soviet Union. But now we have new players entering into the scene. We have China, of course, we have Russia, we have Japan, we have the EU. And we also have new players like the Emirates, for example, or India. So as you can see, there is a huge investment and huge interest on space exploration recently. So what is the motivation behind this? And to give you an idea about this, it's very important to see some numbers, I would say. So for example, just to give you an idea, the global government investment in space exploration reached about $26 billion in 2023. And we are expecting to grow in the next 10 years to 33 billion. So just to give you a rough idea how big money the government is putting into space exploration. As you can see in this chart, this is from a consultant company. You can see that most of the space investment is being done especially to explore the moon. So that's why I put too much emphasis on the moon in this presentation. In fact, over 47% of the future space investment between 2023 and 2032 will be dedicated to the moon or the lunar exploration. As you can see here, the moon is really playing a big role on the next exploration in general. We also have an estimated over 235 missions that are planned for lunar exploration alone, just to explore the moon between 2013 and 2032. You've probably heard recently some new players sending probes on the moon and exploring the moons. So there have been around 335 space missions in the last 10 years up to the next ones. In the addition to the top investors in the space exploration, as I said, new countries and private sector have joined the new space race. As you can see here, this is the top 5 budgeted space explorations. We have the first is the US, China, Europe, ESA, Japan, and Russia. And also we have smaller players like India, for example, or the Arab Emirates or Korea. So here are some recent lunar exploration missions. Probably you've heard from a few of them. We have the new Artemis program from NASA in the USA, where they are planning to return to the moon and this time set a permanent base on the moon or the polar regions to explore the regolith as well as the water exploration there. We have the Chinese program, the Chang'e program. It's entering its 6th mission now, sending probes to the moon as well as rovers. We will see that on the details later. And they even landed in the far side of the moon. Okay, we have another one from Korea, for example, the Korean Pathfinder lunar orbiter that was sweeping all the craters and the southern poles regions. The Emirates also is planning to launch another rover to the moon. It's called the Emirates Lunar Mission. I think it's going to happen soon, maybe in 2025. Japan also sending another probe, the SLIM project, that landed not very successful, but they sent a probe on the moon recently. And also we have India with the Chandrayaan program, impacting the southern pole of the moon so that they can get some particles of water and ice and analyze the ice and water existing on the lunar regions. We also have other missions on Mars, the red planet. So we can name the Tianwen-1 probe from China orbiting the planet right now. The Emirates also launched another probe. It's called the HOPE probe in 2020. And of course, the rovers, the Perseverance rover from NASA, ExoMars rover, Mars Ice Mapper, as well as the InSight lander. So we are going to see the InSight lander much in details at the end of this presentation. So why do we need to mine the moon? Why it is interesting and why people are investing on how we can go to the moon and harvesting the moon there. So usually we go to the moon in order to set a base on the moon for research purposes. We need to understand the geology of the moon, right? This is very important. And also we need to build shelters. So since we cannot really ship all the construction materials from Earth to the moon, then we are planning to use the in situ resources such as the regolith. We will explain what is the regolith. The regolith is the lunar soil, so the dust on the moon or the very top geological layer on the moon is kind of dusty, you know. So they are planning to use this kind of material. It's called the regolith to build, as you can see, shelters, temporary shelters on the base using 3D printing materials. So we need to mine this kind of materials for constructions. Other motivations for exploring the moon and mining the moon is try to extract water. We discovered that we have some ice on the polar regions of the moon, and we are planning to harvest this water for building a rocket fuel, for example, or maintaining and sustaining the lunar base. Also, there is few motivating elements that push us to go and harvest the moon. Is the helium. It's a rare element that is used for nuclear fusion, and also rare earth metals was discovered on the moon, so they can be used in modern electronics such as smartphone computers and other equipment. So you can see the moon is already rich. It's just waiting some bold, I would say, nation or bold people that's going there, try to harvest it and be the first humans on harvesting the moon. And as you can see, things are not science fiction anymore. Things are moving forward, and space agencies, big space agencies, already have a roadmap, setting objectives on harvesting the regolith on the moon. So they already planned what they call in situ resource utilization. It's called ASRU. Basically, it's Can you hear me? Hello? Sorry, I think I have a problem with my phone. No.
Yes, we can hear you.
Oh, can you hear me?
Yes, Mohammed, yes.
Okay, just give me 1 minute. I think I have a problem with my headset, and I'm going back to you right now.
Yes, take your time.
Just give me a minute. Okay, can you hear me now?
Yes.
Yes, we can.
Okay, excellent. Sorry for that. I think my Bluetooth just got disconnected, but I think things are good now. Okay, so I was talking about the space in situ resource utilization. As I said, some space agencies already have drafted a roadmap to explore the resources on the moon, such as the regolith of water. And as you can see, it's starting from prospect, establishing, mining, transportation, refining down to the supply chain. And this is very similar to what we do, for example, in oil and gas, in hydrocarbon exploration. We have a roadmap, we have some kind of stage gates, resources utilization protocol that we try to mimic so that we can use the same protocol for exploration, for in situ resource utilization on the moon. Some people also are talking about mining the asteroids. This is, for me, I think it's still far away, but the dream is here, the ambitions are here. Scientists and interpreters have their sights set on the Wealth asteroid that could bring to Earth, for example, just to give you an idea. The asteroid Ryugu here, as you can see, only this small portion of the asteroid can worth up to 82 billion US dollar. So if you can get back this small portion from the asteroid and get it back to Earth, then you're going to be a trillionaire for sure. Actually, it's Neil deGrasse Tyson who said the first trillionaires will be those who mine asteroids. But again, this is something really new. I'm not sure if there is any proper program to mine asteroids so far because it's very, very difficult. There are only few American and Japanese missions that try to explore the asteroid, understand what they contain so that they can investigate if they can mine them or not. And some world-renowned universities and schools already started their own space curriculum. For example, the Colorado School of Mines in the US, they already started their first space mining program. And they can teach students and they can enroll students to learn how they can mine the moon and asteroids. Right, now we're going to jump to the next chapter, which is an overview of the lunar geology. We're going to talk about our natural satellite, the moon. Right, so this is the moon. This is how we all know the moon. This is actually what we call the near side of the moon. So we have what we call the near side of the moon, and we have the far side of the moon. So there's no dark side of the moon, okay? Because the moon is always illuminated by the motions of the moon toward rotating the Earth. So there's no dark side of the moon. But we talk about the far side and the near side. So why we talk about the near side, it's actually because the moon is gravitationally locked. So we have the impression that the moon is always facing us with the same face. It is actually locked, so it doesn't rotate around itself. We always see the same face on that toward us, right? So if we have to dip into the geology, this is what it looks like. We have some kind of dark colors. It's called the lunar mare. It is basaltic formations. It's lava, okay? And then you have a whiter skin, I would say, or whiter colors, highlands. It's called the lunar highlands. And this is actually made of the ancient crust of the moon. And as you can see the geology here, you can see the red color, which is a lunar mare. It's kind of ocean mares, okay? It's oceans of lava. And you have a very old, structures, which is the lunar highlands. And as you can see, it's always impacted by asteroids and meteoroids all over the time. So you can clearly see the effects of the asteroid hitting the moons over the years because there's no weathering on the surface of the moon. Here are some names of the topography of the moon. Here we have what we call the Mare Iberium, one of the biggest one, the Oceanus Porcellarum. You have the crater Tycho, the Tycho crater, which is very, very bright if you have to see the moon. And we have the Aristarchus volcanic complex here. We are going to talk about it a little bit later. And other minor mares, it's called, as you can see, I always put the name Mare, Tranquillities, Serenatis, etc. Now, if we have to look at the other side or the far side of the moon, this is how it looks. And as you can see, it's more whiter. It's mainly crustal formation, it's crust. And we can see a lot of mare, as you can see on the front side of the moon or the near side of the moon.
This is the geology. It's mainly impacted. Probably two of the main important structures is what we call the Oriental Basin here. It's a hidden basin located at the rim of the moon, as well as the Southern Pole or Aitken Basin. This is where the Chinese rover U2 is running now on the moon. Right, so if we have to develop the lunar geology on the unified geological map, actually USGS already did this. And if you have to deploy all the geology of the moon, this is how it looks. And as you can see, we have a near side, which is made of lunar mare and basalt formation. And the other sides are made of very, very thick crust. So if we have to make a cross section through the moon, you can see that the moon crust is disproportionate. You have a very thin crust near side. You have a very, very thick crust on the far side that can go up to 100 kilometers here and 60 kilometers here. So as for now, we are not sure. I think we are not sure if there is any tectonic activity on the moon. We believe that there is no tectonic activity on the moon, but we do have moonquakes, and we will explain where the moonquakes come from. So based on the moonquake studies, we already derived the velocity profiles of the moon, and we roughly describe the interior structure of the moon, which is not yet 100% accurate because of the lack of data. So until today, we're not very, very sure what is the moon made of, the interior. So here are some lunar landscape, I would say, or some geology you would see on the moon. We have, as I said previously, the lunar highlands. It is an ancient crust made of, it looks like a sponge structure. We have the lunar mare or the basaltic lowlands here. And also we can see a lot of craters from different ages. You can see different craters of different size as well as different dates. And finally, all this surface of the moon is covered by regolith, which is a very, very small and thin, I would say it's powder, I would say, or just the soil. We call it soil, but it's not really soil properly saying, because actually it's just dust, okay? So if we have to look inside this soil, the regoliths, it's covered by a layer of, it's basically an unconsolidated debris that goes a thickness from 5 meters to 10 meters. There is this representative schematic representation of the lunar regolith. As you can see, we have the fractured crust, and that's going to be more and more fractured the more we approach the surface, until we reach a very, very thin layer of regolith or lunar dust. So since the moon lacks any sort of atmosphere, there is no erosion, there is no weathering, and the upper few millimeters of the regolith is exposed to the bombardment of micrometeorites as well as solar wind. And that's what explains all the abundance of this regolith on the surface of the moon. If you have to look at the regolith under the microscope, this is how it looks. It's typically agglutinated particles that really stuck into any material we send there, because it's very static, as I said, and it's really, really problematic if we plan to go to the moon. The moon, we have better understanding of the lunar mineralogy of the surface of the moon. The moon mineralogy mapper, the Chandrayaan-1 spacecraft from India, already mapped all the surface of the moon as well as the composition of the mineralogy. And the lunar magma ocean hypothesis envisages that the moon was completely molten to hundreds of kilometers depth immediately after its acceleration. So the major minerals crystallizing from the LMO, or the lunar magma ocean, would include olivine pyroxene as well as plagioclase. Okay, now let's talk about geophysics. And now that you have a better understanding of the geology of the moon, we are going to talk a little bit more about the different geophysical data we have from our natural satellite. Of course, I will start with the Apollo missions. The Apollo missions is the space program by NASA, where they sent astronauts to the moon several times. So we have 6 different Apollo missions, starting from the Apollo 11 and ending by the Apollo 17. So the interesting thing is that during the mission Apollo 11, 12, 14, and 15, astronauts took with them what they call a passive seismic experiment, or PSE. As you can see in this picture, this is the astronaut here. This is, I think, during the Apollo 14 mission. And this small instrument actually was designed to record moonquakes. We're not talking about earthquakes, we're talking about moonquakes. We're talking about, they measure the seismology of the moon, the seismic activity on the moon. And as you can see, these are the different Apollo missions. We already have recordings at Apollo 16, 15, and 12, and 14. Apollo 11, the first mission, actually, the PSE, the Passive Seismic Experiment, only functioned for about 3 weeks and then stopped due to technical difficulties, but the others, luckily, were good enough to record an interesting database. So this is how the moonquakes were recorded back in time. The origin events were detected by eye, and they were recorded using this kind of big old magnetic band, I would say, and then treated using these huge computers, and all the moonquakes were studied by hand, as you can see. So recent reanalysis focused on the application of modern computer capabilities and techniques that were not available back during the Apollo missions. And now we modernize, I would say, or digitize all the PSE, the Passive Seismic Apollo Missions catalog in computer. So the PSE station consists of 3 components. So mid-period displacement seismometer, 2 horizontal and 1 vertical, similar to what we have here on Earth, as well as a frequency bandwidth that have a frequency bandwidth between 0.1 hertz and 3 hertz. So this is basically the mid-period PSE component. It's recording events from 0.01 to basically 3 hertz. So it's mid-period seismometers, as well as a unique short period vertical component. You can see it here in blue, that is recording frequencies from 1 hertz to 10 hertz. So unfortunately, we have only one component. It's only recording the vertical motion. But however, for the mid-period displacement seismometers, they can record both 2 horizontals and 1 vertical. So this is how the moonquakes looks like. This actually, we do have moonquakes. We do have the seismic activity on the moon, which is basically caused by meteor impacts, as well as some deep moonquakes and shallow moonquakes. Until now, we are not sure what causes these deep moonquakes and shallow moonquakes. But some people say some scientists think that it's due to the motions of the moon when it's rotating around the Earth, and the proximity to the Earth. It's, there's some kind of attraction that displaces the moon that change the elasticity of the moon and provoke some earthquakes. But there's no proper tectonic as we know here on Earth so far. As you can see, if you are good on seismology, these are actually minutes. So the difference between moonquakes and earthquakes is that the moonquakes are really long. So they can take, the moonquakes can take up to 2 or 3 hours of recording of the same event. And luckily, the Passive Seismic Experiments Network recorded more than 30,000 seismic events between deep moonquakes, shallow moonquakes, meteor impact, as well as other unknown and unclassified events. So as you can see, this is a small comparison between the moonquakes and the Japanese earthquake in 2011, the Tohoku earthquake. So as you can see in Earth, earthquakes usually last less than 2 or 3 minutes. It's really less than 1 minute. However, on the moon, it's going to ring for about 2 or 3 hours of continuous motion. We are still not very, very sure why on the moon we have such a ringing effect of the moonquakes, but it's probably due to the lack of subsurface water and also the heavy, extremely fragmented regolith near the surface that are going to create some kind of resonance inside the moon and makes the signal or the moonquake last much more longer than what we experience here on Earth. We also have some active seismic experiments. These are actually seismic refraction data that were generated by the astronaut on Apollo 14 and Apollo 16 and Apollo 17 missions. As you can see in this picture, there is an astronaut here holding a thumber, some kind of explosion device that generates vibration at the surface of the moon. And then he put a long rope, as you can see, lined with geophones and recorded the shallow response or the shallow arrival time of the thumber that generated. So this actually helped us to map shallow depth down to 460 meters of the regolith. And the seismic energy source used was a thumper, as I said. You can see it in this picture here, this white box that helps to generate vibration. And this is actually the same note that were taken to the moon and get back on Earth during the Apollo 16 and 17 missions. Right, so just out of curiosity, this is how the seismic refraction profile looks like. These are the seismic recordings at the geophones from the thumber, right? As you can see, sometimes it's not very, very clear. And thanks to this active seismic experiment, some researchers successfully determined the VP, the velocities of the lunar regolith. For example, this is Apollo 14 in the Fra Mauro formation. So they estimated a VP of 100 millisecond on the lunar regolith, which is estimated around roughly 8.5 meter. And then you have the whole Fra Mauro formation and then going down to 80 meters. So thanks to these numbers and these active seismic experiments, we successfully determined the shallow velocity structures at the Apollo landing sites. Okay, we do have also another very interesting geophysical data on the moon. It's called gravity data. So NASA sent a dual lunar orbiter called the GRAIL mission. It's called GRAIL, stands for Gravity Recovery in the Interior Laboratory, sent by NASA, that orbited the moon and then tried to map all the gravity as well as the topography of the moon. As you can see, now we have a full map of the gravity and the anomaly, the boogie anomaly of the moon, thanks to this mission. And the good news is that on December 2012, NASA released the gravity map of the moon. So all these data are open source. You can use them, I can use them, we can download them, and we can maybe push the science forward using this data. And by the way, even the Apollo missions, many Apollo passive seismic experiments, as well as active seismic experiments, are open source. They are public, so everyone can use them now, can download them and try his idea or her idea on this data set. There is another probe, a Japanese probe, this one. It's called the Selene or Kaguya mission. Selene stands for the Selenological and Engineering Explorer. In Japanese, it's called Kaguya. And it is administrated by the Japanese Space Exploration Agency, JAXA. Basically, what they try to do, something similar to what NASA did with the GRAIL mission, but I think this one is prior to the GRAIL mission. So we first had Kaguya space mission that tried to measure all the gravity on the moon. And as you can see, we have a low resolution lunar boogie anomaly of the far side of the moon as well as the near side of the moon. This is how the Selene space probe looks like. And then we have the Chinese rovers, the Chinese program. There are many Chinese missions, but I'm just going to talk about 2 or 3 of them. We have what we call the Chang'e 3 mission. It is a robotic lunar explorer mission operated by the CNSA, the China National Space Administration. It was launched in December 2013, and it's incorporating a robotic lander, and it's China's first lunar rover. It's called the U2 rover. This is how the rover looks like. And it landed on the Mare Imbrium. This is where the Mare Imbrium is. It's in the near side of the moon. And the good thing with this rover is that in order to improve our understanding of the formation of the moon, one of the payloads or one of the instruments of the Chang'e 3 rover, this very small rover here, it contained a lunar penetrating radar. It's actually a GPR. It's a ground penetrating radar. It looks like it's very similar to what we do here on Earth. But just call it lunar penetrating radar. And this investigation is the first attempt to explore the lunar subsurface structure by using ground penetrating radar with high resolution. So just if you are wondering what's the lunar penetrating radar looks like, there is a paper on this. There are many papers actually. This is actually the rover trace. This is the distance crossed by the rover from its starting here, and then it traveled all this path, and all along this path, as you can see, it's used a radar. It looks like seismic actually, a very high frequency seismic that can help you to map the subsurface of the regolith, as you can see. And we already start doing interpretation based on this lunar first. It's not seismic, but radar subsurface data. For example, the stratification of the regoliths along the U2 rover's transverse path with the assumption that the regolith has a relative dielectric constant of 3.1. As you can see, this is the structure of the regolith at the shallow parts of 2 meters. And the arrows here indicate that the layer of the regolith where the thickness of the regolith is 4 to 6 meters. So that means that we have some thickening of the regolith at some places. And the region labeled by A here has a typical hyperbolic shape, as you can see. That might be caused by a rock underneath the regolith. So probably there is some buried rocks here. So as you can see, it's very, very irregular, and it's very, very difficult to map as well because we are dealing with very, very thin regolith here. Okay. Then we have another space mission from China, the Chang'e 4 this time. It was launched on January 2019. and it's successfully landed on the eastern floor of the von Karman crater. The von Karman crater is located here at the far side of the moon, at the southern part of the the far side of the moon. It's called the Pole Aitken Basin here, and it was like one of the, I think it was the first far side landing with a rover. It was successful, so it was historical. This is an on-site picture of the lander on the Aitken Basin on the von Karman crater, taking a picture of the U2 rover. I think it's the U2 rover as well, using an onboarded camera, as you can see here. So yeah, this one is called U2. This one is U2-2. Sorry, U2-2 rover. The U2-2 rover also contained a very high frequency GPR, ground penetrating radar, and the observations were also revealed and showed the detailed subsurface structure at depth down to 40 meters at the von Karman crater on the far side of the moon. This is how the Chang E4 GPR image looks like. It provided a clear information about the structure of the subsurface. As you can see, it looks very similar to seismic data here, and we can already see layering, down to 450 milliseconds. The interpretation gives this. You have 3 units. Unit number 1, 12 meters. The second unit's around 24 meters, and then down to the third unit's around 40 meters. As you can see, there is some kind of poor reflections here. We still don't know what it is. This probably something related with the lunar ejecta, because we are in a crater, so we probably have some kind of ejecta that are laying that on the subsurface. Okay, also there is a huge interest on exploring the lunar poles, ice exploration, because we discovered that there is ice on the lunar pole, at the southern pole and the northern pole of the moon. Especially NASA is really interested to go there because we want to harvest the water there. It's sustainable for life because we have water. Ice means water. We just need to know what it is made of, what kind of chemicals it have, and how we can explore it, right? So most of the ice was found in surface craters, as you can see in this representation image, but are never touched by direct sunlight. So this is what explains the existence of ice there, because basically this top and bottom side of the moon is never hit by this direct sunlight. So we have some kind of permanent shadow zones, right? Permanent shadow craters that are never touched by sunlight, and that's why they contain water. So they can hover around minus 155 degrees Celsius through. Not all of these cold traps contain ice, but the scientists are still exploring until now. So these pockets of ice are interesting. As I said, it's because they can provide scientists with valuable clues about the composition and activity of the moon, as well as water to be used if we want to set any basement there. Okay, now we talk about other planets. We talk about the geophysical exploration of Mars and Venus. We first start a little bit about geology about the red planet, Mars. As you can see, this is a topography map of Mars. And probably the first thing you can observe here is that we can divide the Martian planets into 2 geological distinct areas. We have on the north, you have lowlands, or what we call oceans, I would say. And at the bottom, we have a high elevated area. So it's really disproportionate between north and south. We still don't know why. If you see this side of Mars, you can see that we have a high elevation, or like rising a big, we have big mountains, I would say, or mountainous area. This is where we find, and also this area is associated with a very intense volcanic activity. This is where we find the Olympus Mons, by the way, as well as the Therasis region, which is made of many, many volcanoes. This is the most famous area maybe on Mars, the Valles Marineris, which is a huge canyon. As you can see, basically this area is really elevated compared to what we have on the other areas. And interestingly, this area, if you have to see Mars in 3D, like a global planet, you see that this elevation is counterbalanced by a very, very low depression here. It's really opposite. It's really the exact opposite of it. We found what we call the Hellas Planitia, which is a depression, I would say, balancing, the big mass we have, the big elevation map we have in this area. So as you can see, Mars is very, very interesting. We still not sure if there is any seismic activity on Mars. We know there is ice. We know that there used to be water before because we found a lot of trails of water, old rivers, old canyon dug by rivers back then, but we still don't know where the water of Mars is. Some people said probably it's all escaped inside the planet. Some others say it was just evaporated out of the blue. But we still don't know where the water of Mars is, but we do know that it contained water at some point. Why we call it the red planet? Because of the red color. As you can see, it's very, very dusty environment, where we have a common sandstorms and dust storms. And actually, we do have a few missions on Mars as well, from the US and the Soviet Union. We have, for example, the famous ones are the NASA rovers, the Perseverance here, the Opportunity rover here. We have another one, Pathfinder. We have older mission, Viking 1 and Viking 2, Phoenix, Spirit, and Curiosity rover here. Right, let's talk about geophysics again. So seismology on Mars was a succession of failure missions. Mars is very, very difficult and very, very hard. Why? Because first thing is actually it's very far compared to the moon. You need to really have specific time of launch. You have really to master your probes when you send them to Mars. Also, landing on Mars is very difficult because the atmosphere of Mars is very, very thin compared to Earth. In the moon, we don't have any atmosphere, right? So in Mars, it's very thin, so you cannot really slow down your probes when you send them there. That's why you see all this kind of ingenuity when we try to send the rover. When NASA sent the rovers, they developed a whole complicated system made of parachutes and then a crane, and then the crane, you're going to fly a little bit before landing, before dropping the load onto the Martian surface. This is because the atmosphere of Mars is very thin and you cannot really slow down your probes when they enter the atmosphere. So as I said, it's a succession of failures. The first mission on Mars, it was not the first one, but the first containing some geophysical evidence was the Viking program, where 2 probes were sent into Mars, the Viking Mars program. This is the picture that successfully landed. I'm not citing here all the mission that failed, that crashed, right? These are the mission that successfully landed on Mars. So we had the Viking Mars program in 1976. It contained a seismometer. This is a picture taken from the lander. And this small box here, this is actually the seismometer, which aims to record seismic activity on Mars. Then we have the Mars 96 mission by the Russians. Again, it was a failure. And then finally, the first time we successfully sent a probe and not a probe, but a lander on Mars and recorded the Mars quakes was the InSight lander mission in 2018. Okay. So the Viking program consisted of a pair of identical American space probes, Viking 1 and 2, which landed on Mars in 1976. The lander carried an instrument to achieve primary scientific objectives of the mission, including a seismogram, as I showed before. Although the lander were operated for several years, the seismographs were mounted on the top of the lander, and this is what it was a problem. And they were unable to detect any clear seismic activity because they were not paired with the ground. They were only at the top of the lander, so they couldn't really record any significant activity. The Viking 2 device collected data for about 89 days of data over 560 sols. So sols, S-O-L, is day, right? It's Martian day. We don't say day, we say sol, because the Martian day is longer than the Earth day. So over 560 sols of lander runtime, and the Viking 1 lander did not return any data due to the problem activating the seismometer. However, there is only one suspected event from these 2 missions. So on Sol 80 in November 25 in 1976, a single seismic event, as you can see here in the recordings, was recorded, which bore the signature of an expected Mars quake. So we can say probably that was the first Mars quake recording, evidence of occurrence of seismic activity on Mars. Unfortunately, there were no wind data taken at that time, so we could not really understand if it was probably really due to a Mars quake or is it just the wind who did this. So as you can see, this is the vertical axe and the horizontal axe, and you can see a peak of amplifications probably due to a first Mars quake. But again, since there was usually what they do, they record the winds and then they calibrate and correct with the seismogram to see if there is no wind effect on the seismogram. Again, Mars is very windy, you know, it's very, very dusty, and it's very, very difficult to do a proper measurements of earthquakes, of Marsquakes, because of all this kind of noisy environment. We also then have Mars 96 mission. It's also called Mars 8. It was a failed Mars mission launched by the Russian Space Forces and not directly related to Soviet Mars probe. So Mars 96 was intended to solve several problems concerning the understanding of Mars, including the inner structure of the red planet and the igneous crust. However, unfortunately, and also the Mars 96 also had a seismometer. However, due to problems, the probe didn't really achieve all the missions. And then finally, probably the most successful seismic mission on Mars was the InSight lander. It landed in 2018. Actually, it was expected to use seismology to elucidate the structure and the formation of the red planet. As you can see, it's made of like huge landers specifically dedicated to study Marsquakes. Now, as you can see, there is some kind of this kind of small sphere. This is where the seismogram is. And at the landing, you know, the robots, there is some robot arm that took the seismometer, place it on the ground, and then cover it directly with this cover, as you can see, so that they can avoid the Martian winds, okay? And then we can have a clear response of the grounds during Marsquakes. And you know, the InSight Mars lander was successful and brought the first Marsquakes, I would say, recordings. Now we know that there are Marsquakes, there is seismic activity on Mars as well, and we had a huge catalog recorded by the InSight mission. The good thing is that the interesting thing is that Marsquakes have a characteristic already observed on the Moon during the Apollo, which is a long signal duration of up to 10 to 20 minutes due to the scattering properties of Mars. So we observed the same long period, I mean, long shaking Marsquake, similar to what we observed on the Moon. And just to give you an idea, all right, this is an earthquake. This is in Switzerland, okay, the 50-meter distance. And this is actually the scale in seconds. And as you can see, the earthquakes looks very, very punctual. It's just a small earthquakes. However, moonquakes, distant moonquakes, may last longer. This is another earthquake in Greece. This is really, really long, but Marsquake, as you can see, they're going to last longer, and they give similar signature to what we see on the Moon as well. So this is also a frequency spectrum of the recording of the Marsquakes. As you can see, just during the deployment, the instrument started recording here, the first recordings here, and you can see this is the robotic arm. This is the robotic movement that took the instrument and set it on the ground here, recorded. And then the instrument already started to record first Martian events or Marsquakes. And you can see here the wind. The Mars winds can appear on the seismogram as well. And we can filter it after this. And also we can use only so that we can extract the Marsquake and then use it from the background. We also have something similar to what we have on the Moon, which means a gravity map of the Moon. And this is what we call the Goddard Mars model, GMM, sent by NASA. It was recorded by the Mars Reconnaissance Orbiter. And we now have actually all the gravity as well as the topography of the red planet thanks to this mission. And the good news again is that all these data are open to public, so you can download them and then you can bring your own ideas on the table to advance research in this topic. Okay, last but not least, Venus. Actually, we don't have many missions to Venus. It was actually especially the Soviets or the Russians who tried exploring Venus by sending the Venera program. So the Venera flew the GROZA 2 instrument. It's a combination of a microphone and a rudimentary single-axis seismometer able to measure vertical displacement on the visual surface to micron precision. So we had our first seismometer on this probe attached to a ring around the probe, which was in contact with the surface. The GROZA 2 seismometer coupling with Venus was less than perfect. The landing was very good. The very short lifetime of the two stations was also a major drawback of the measure. Unfortunately, this mission didn't last long, you know, just few days, I think. And we only had 1 or 2 or 3 pictures from the lander. This is probably the first and last picture on the Venusian surface on Venus, taken by the GROZA-2 lander. GROZA-2 managed to send some data back to Earth, but their interpretation ran up against the same problems than the Viking, and we lost contact with the probe. So unfortunately, the landing was good, but we lost contact, so we don't know if there is any Venusian quakes, I would say, or any seismic activity on Venus, despite that we had a seismogram on place. Okay, so now I would like to share with you some case studies I was involved in and published on geophysics, how we use geophysics for planetary exploration. I will start with actually, I've been working in this for a few years now, trying to use all the open source data I was showing right now to understand what the subsurface of the moon looks like. This is one paper I published in a conference in Abu Dhabi, Lunar Oriental Basin Subsurface Structure Estimated from Kaguya Orbiter Data Inversion. It's co-authored by another friend and colleague of mine, Professor Hakim Saibi. So basically what we did, we used the Japanese Kaguya gravity data and tried to understand the structure of what we call the Oriental Basin of the moon. If you remember, I showed you the far side of the moon, there is Oriental Basin. The Oriental Basin is actually a multi-ring basin that is very, very new and it's very, very clear on the moon, but we still don't know how these basins are formed, we still don't know the structure of the... So what we did, we took the gravity from the Japanese probe, and then we used Petrel here so that we can reconstruct the subsurface density inversion. And this is how this is the crater, this is the Lunar Oriental Basin looks like. This is a north-south cross-section, and as you can see, we correlated surface discontinuities or surface what is suggested to be some kind of faults connecting the mantle to the surface. And this is probably explaining the connectivity of the mantle uprising through this multi-ring basin up to the surface using gravity inversion. I do have another research on another topic. This one, probably this is one of my proudest papers. I did it with NASA. I collaborated with NASA. So they sent me the seismometer recordings from the passive seismic experiments on the different Apollo missions. And I was the first to discover or to quantify the effects of the lunar near surface geology on these moonquakes recordings. So imagine the moonquakes were there for more than 50 years and nobody thought to use this kind of methods. We discuss in our paper so that we can understand the effect of the geology on moonquakes ground motion. So we used, I will not go into too much technicalities, but what we try to do, basically try to see what kind of geology is affecting the amplification of moonquakes using meteor impact data from the passive seismic experiments at different Apollo missions. We used Apollo 12, 14, 15, and 16, and then we used some techniques that can help us to quantify the near-surface geology effects, such as the H/V spectral ratio or the reference site methods. And then we ran some numerical experiments and proved that, okay, the geology is actually affecting the amplification of moonquakes at specific frequencies when we change from one site to another. And then finally, this is another one. The same year, 2022, I collaborated with the University of Wuhan so that we can understand more the volcanism on Mars. And we basically worked on this structure. As you can see here, this is the Elysium Rice, if you remember. It's the largest volcanic province on Mars. To understand the volcanic activity of this area, we use the bouquet gravity data derived from the GMM3 models, and then we try to estimate the subsurface mass, the subsurface mass of this volcanic area province using the Goddard Mars model. So this is published in Icarus, and if you're interested, I can send you the paper. And then finally, my latest publication, again, this was in GGR Planets, detection of subsurface density structure of the Aristarchus plateau by gravity inversion. This is, again, probably this is the first academic paper or research paper published on the moon using Petrel. So I used Petrel as a tool to explore and map the subsurface structure of the Aristarchus plateau. This is the Aristarchus plateau. It's a volcanic complex on the moon. And we derived the first subsurface density contrast with of this area. And we published this in JGR Planet. I don't want to bother you with too much details about this, but just think about that. We use the Grail data I explained before. I feed it into Petrel, and then thanks to Petrel and the inversion algorithm in Petrel, we discovered the subsurface structure of this volcanic complex on the moon. Again, it's in JGR Planet. If you're interested to learn more about it, let me know. Okay, so before closing this course, I would like to give you a gift. So the good news is that now we have many open source data. Most of the things I was showing here, or the missions I was sharing with you guys, are now public. That means you have no excuse. You just need to go to these websites, one of these websites. You can go to the NASA Planetary Data System PDS, and then you can download all the NASA missions data raw, okay? Whether it is gravity, seismic data, lunar topography. You can even download something not really related with geophysics, maps, etc. There is another very interesting tool. It's called ActReact Quick Map. This one, you can just go to this website and visualize the moon on 3D as well as the different data on real time. You can also use the Lunar Orbiter Data Explorer, as well as the high-resolution lunar topography. And for the Japanese one, is the Kaguya Gravity and Topography Data Download. So you can download the data, okay? And then you can already start trying things. So thanks to this data set, I published all the research in cooperation with different universities and research institutions, as you can see. All right, so I think it's almost time. I've been talking too much. Yeah, just a few takeaways for you guys. The good news is that the era of commercial space mining has begun. Government are very serious about this, researchers as well, putting a lot of effort to understand how we can mine the moon and how we can understand our planets, especially with the advent of the in-situ research exploration. Again, geophysical data available on planetary exploration mainly consists of seismic data, gravity and rovers, rather measurements that you can download, you can access, and you can already use for your studies. And then finally, the moon remained the most affordable and the most well-known celestial body for geophysical studies, while we are only at the infancy of planetary geophysics. Thank you. Thank you very much for your kind attention. Any comments or questions are welcome.
So thank you so much, sir, for this great lecture. So guys, if you have any question, please don't hesitate to ask it. Actually, you have a question in the chat box, sir.
Oh, we do. Okay, I didn't. Let me check that.
Yeah.
Okay. Hello, Dr. Amrouche, or is it? Do you think that? Okay, I'll start with the first one. Do you think that the next step for technology providing companies, as in SLB, is to invest in providing services for space exploration? Thank you for your insight. Okay, thank you for very good questions. Yeah, actually, my company, SLB, is already opening new frontiers for providing services at different levels, not only space, but for example, we are now working on geothermal, working on green energy, hydrogen, etc. So yes, probably there would be some big investment on space exploration as well, but not for the immediate actions, because we are not on the moon yet. Okay, so we're still at the exploration stage. There are some things we can do, for example, using the technology that USSLB is developing to accelerate. So yeah, that's something that is already being done so far. Please, Dr. Amrouche, can you share the links? Source? Yeah, of course. I think you can just take a snapshot. Let me just go back to the slides. You can take a snapshot of this. Okay, I will leave it for you like for 3 seconds. You can just take a snapshot of this from using your smartphone, or just type keywords, search on keywords on the internet. NASA Planetary Data System, ActReact, Quick Map, Astropedia, Lunar Orbiter, high-resolution light topography, and finally for the Japanese data, Kaguya Gravity and Topography Data Download. Right, I think it should be enough. Yes, other questions as well. Let me see. Let me go back on Zoom. Hello, sir. It's such a pleasure to learn from you. Thank you. My question is, as a mining engineer, is planetary mining very different from the one we already do? Can I convert to it after graduating? Second question is, okay, let's start with the first one. Well, this is something we are all learning now. We are not the only one asking these questions. So all the scientific community is learning. So we don't know yet if the mining on the moon is going to be similar to Earth. But what we are sure about is that we are going to use the knowledge or the expertise on the mining on Earth and apply it to the moon, okay? So it's going to use our know-how on Earth as a trampoline, and then we are going to convert it to the moon. Probably one of the challenges we are going to face is probably logistics. We cannot transport big, instrument, big car, big excavation stuff to the moon. So this is going to be very, very difficult to achieve. Probably we just can't afford small robots so far. And also the lunar dust is going to be very, very difficult because it's going to stick everywhere and probably stick onto the robots we send there and block the system. But again, we don't know yet. We still didn't start it. This is something subject of research, and many research are being done in this direction. Second question is planetary mining more sustainable? If yes, how so? What do you mean by sustainable? So, well, we are going to mine to build there. We are not going to mine to bring back to Earth yet. So there is no carbon there's no atmosphere to pollute on the moon. There's no rivers to pollute, as far as we know. It's a vacuum, so yeah, we cannot talk about pollution on the moon. So it should be very, very sustainable because we are not even in our own planet. I hope it answers the questions. Okay, what is the key difference between the seismometers used in other planets and those used on Earth? They are pretty much the same. We use the same concept, probably just fewer developments, few add-ons, I would say, on the instruments. But basically, we are using the same instrument. We use the here seismometers we use here on Earth. That means a triaxial component measuring the motions horizontally and one vertically with a large band of frequencies to record the earthquakes. We use the same concept. Actually, there is another project from NASA. They're expanding their lunar seismic network by 2025, I believe. So next year, probably, are going to send some missions to deploy new seismic network on the moon as well. Yes, do we have any other questions?
So, sir, I have actually a simple question.
Sure.
Is the moon relatively geologically stable, or do its layers change like those of Earth?
Yeah, good question. We still don't know. We know that there is no tectonic activity on the moon. It is relatively stable in a sense that we don't have subduction and abduction like we do have with tectonic plates here. So we don't have tectonic activity yet. But for the layer, for example, do we have a clear core? We're still not sure about this because we have very, very few recordings from the moonquakes, and the gravity data do not really show very, very deep structures. So we can just speculate so far about the inner structure of the moon. Okay.
So, guys, if you have any question, please ask it.
Sure.
Hello.
Hi.
Hi, Dr. Amrouche. Really fun to see your presentation. I'm a huge fan of your work. It's very interesting. I mean, to see what we can do with planetary geophysics. I have a sort of a question, but it's more about like access to these resources that we have on other planets. Like they are the property of what a country exactly? Like, is it something that has to do with the first that has arrived there, the first served, or is it? Is there any political?
You mean legislations and politics?
Yeah.
To be honest, I have no idea about this. I know that it's the golden rush. It's as we it's a new golden rush to who's going to be who's going to plant his flag first there. But so far, as far as I know, there is no international consensus about this. There are some regulations on how to, for example, how to explore Antarctica, or places where nobody belongs to nobody, but for the moon nobody knows yet. So that's why people are really rushing there. But I think it's as first arrived, first served, right? Especially if we start seeing people landing there and setting bases, there will be some international laws and regulations that are going to regulate hopefully all this. But yeah, that's very interesting moments now, because we are really at the early stages of the new space race. The next decade is going to be very, very interesting in this direction.
Yeah, and do you think Algeria should come in and try to do something with that?
Well,
do you think we have what it takes to do that?
Well, I'm Algerian. I live in Algeria, and I did it. So you guys can do it. It starts from here. It starts from doing your own research, trying your own stuff, using open source data, collaborate with NASA, with some universities, and that's it. I published around 5 papers on this. No, that's 4 papers on just using this, and I'm Algerian. But Algeria as a nation, for example, Algerian Space Agency, I don't think we have enough political, mechanisms that help us to do this. But, at our levels, at personal levels, we can always do things. Do you have any other questions?
So, guys, we have now reached the end of this lecture. I would like to take a moment to express our gratitude to Mr. Mohamed Amrouche for dedicating his time to share this valuable research with us. Thank you so much, sir. And thank you, everyone, for joining us today. Thank you.
Thank you, Shaima. Thank you for this opportunity. Please keep on doing this kind of lectures. It's very, very inspiring. It's very beneficial for all the community. So thank you for your efforts. Thanks.